The topic today I gonna take is AD converter, analog to digital conversion. Analog to digital converter. Terminologies. Analog. A analog signal is a continuously valued signal such as temperature or speed. A digital signal is a discrete value signal such as integers encoded in binary. So let us take analog signals. Analog signals are directly measurable quantities. Example, thermometer. Mercury height rises as temperature rises. Next one, digital signals. It has two states. One is 0 and the other one is 1. 1 can be determined as on state and 0 can be determined as off state. Example, light switch. So the light switch can either be on or off. ADC basic principle. The basic principle of operation of ADC is to use the comparator principle, that is to determine whether to turn on a particular bit or not. It is typically for an ADC to use a binary digital to analog converter to determine the inputs to the comparator. Next one, quantization. Quantization is nothing but, so there are several processes involved in analog to digital conversion. One of such processes is quantization. Quantization is nothing but the process of converting the sample's continuous valued signal into a discrete valued signal. That is, a continuous signal is transformed into a discrete signals. So it has a process called quantizing. Quantizing means breaking down a log value into a set of fine states. For example, the number of possible states that a converter can output is n is equal to 2 to the power of n, where n is the number of bits in the AD converter. So for a 3-bit AD converter, n is equal to 2 to the power of 3 is equal to 8. Analog quantization size. So the analog quantization size can be of 1.25 volt. So with this quantization, so here look at the diagram of the A to D conversion. So for a given input x of t, we get a 8 bits output. So this is the process of quantization represented in the diagram. Now for now we can explain the analog to digital conversion steps. First one is the quantizing, that is breaking down analog values into a set of finite values. Next one is the encoding, which means that assigning a digital word or a number to each state and matching it to the input signal. Step 1, quantizing. For example, if you have 0 to 10 volt signals, then separate them into a set of discrete states. For example, 0 to 10 can be separated as one with 1.25 volts, that is 0 to 1.25 volt is the first set and 0 to 1.25 to 0.5 is the second set, in such that we can divide the signals as of with 1.25 volt, which is the quantization size already we determined in the last slide. Next one is the encoding. Encoding, we assign a 3-bit digital value to each state that we lastly quantized. That is, for example, for 0 to 1.25 volt, we assign a state called 000. So this is the first bit. So in such way, we assign a 3-bit to the each state. Next one is the sampling process. It is a process of taking a sufficient number of discrete values at a point on a waveform. So with this, we have 3 types. One is flash type, and the one is ramp type, and the other one is successive approximation type sampling. So here the diagram explains the sampling process. So at various points we obtain a data representing it to a continuous time signal. Next one, flash type ADC. Flash type ADC has a series of comparator, each one comparing the input signal to a unique reference voltage. So how the flash works is an analog input voltage exceeds the reference voltage at each comparator. The comparator output will sequentially saturate to a high state. So the priority encoder generates a binary number which gives the output. So this is the flash type ADC circuit. Here we have so much comparator. At each time if the reference voltage exits, then we have an output at the comparator which is dedicatively given a output, that is D0, D1 and D2. Now the advantages include simplest in form, disadvantages lower resolution and expensive. Next one is the dual slope ADC. Dual slope ADC is also known as counter ramp or digital ramp ADC. A dual slope ADC is used in measurement and instrumentation. The dual slope ADC works as in the following manner. When an analog value is applied to the capacitor, it begins to charge. The counter continues to count until it reaches a predetermined value. Once this value is reached, the counter stops and it is reset. As it is reset, the capacitor discharges and the counter stops. When the capacitor voltage reaches the reference voltage, the counter stops and the value is stored in the register. So this is the dual ADC circuit. Here we have a switch and two types of comparators. So the counter and the register mainly works as a function of the dual slope ADC. Next one is the successive approximation type. Comparatively with the other two types, this is much faster than the other ADCs, hence it is most widely used. Here we use a comparator and the DAC. In the process, a successive approximation register is added to the circuit. Instead of counting up each binary sequence, this register counts from the most significant bit and finishes at the least significant bit. The register monitors the comparator output to see if the binary count is greater or lesser than the analog signal input and adjusts the bits accordingly. So this is the successive approximation type ADC circuit where we use a DAC, that is digital to analog converter, and the register. So here we have the ADC types conversions. First one is the dual slope type, other one is the flash type, and other one is the successive approximation type. Comparatively, successive approximation type has much resolution and fast. Okay, also it is low at cost. Examples of ADC applications include microphones, train gauges, thermocouple, voltmeters, and digital multimeters. Thank you.